Alright, so I'm going to start this video at example 3 again. I know we finished some of it in class, but I'm going to redo it for fun. So remember it said, let f of x be sine of x squared plus cosine of x. And we know that the graph of y equals f fifth to the x is shown below. So let's first write the first four non-zero terms of the Taylor series for sine of x about x equals 0. So even though it says Taylor series, we know that this is a Maclaurin, and write the first four non-zero terms of the Taylor series of sine of x squared. So we need our Maclaurin series for sine of x before we can do sine of x squared. So here is sine of x. Remember, it starts at x and it's all the odds. And now we can plug in our sine of x squared, our x squared into all the x's. And we clean it up. Alright, so far so good. This is for sine of x squared. Next up, we want to write the first four non-zero terms of the Taylor series for cosine of x about x equals 0, so the Maclaurin of cosine of x. And we're going to use this series and the series of sine of x squared found in part A to write the first four non-zero terms of our Taylor series for f, which was sine of x squared plus cosine of x up here. Alright, so we know that cosine of x is equal to 1 minus x squared over 2 factorial. So remember, it starts at 1 and it's all the even components of the Taylor series. And now, basically, I want to add the 2 up. So sine, make some space. So we're going to do our sine of x squared plus cosine of x so that we can get our f. So sine of x squared was x squared. Well, actually, scratch that. I should start with this 1 because it has to be from lowest in ascending order, right? So 1. And then next up, we're going to add our x squareds together. So we're going to do plus this x squared from sine of x squared minus, because that's a negative, x squared over 2 factorial from the cosine of x plus the next term, which is x to the 4th. I'm going in ascending order, right? Standard form. Plus, there's no other x to the 4th here, so we're not going to write anything else. Plus the next one, which is the x to the 6th. So negative x to the 6th from here, and negative x to the 6th over 6 factorial from here. Now it said the first four non-zero terms, so unless these cancel out, here are my first four non-zero terms. I just got to clean this up now. So once you clean this up, you get 1 plus 1x squared minus a half x squared, which gives us x squared over 2, plus x to the 4th over 24, 4 times 3 times 2. And then over here we get negative x to the 6th over 6 minus negative x to the 6th over 720. So So once we get a common denominator, so just some side work, negative x to the sixth over 6 minus x to the sixth over 720. When you get a common denominator, you multiply this by 120 and this by 120 to get a 720. So you get negative 120 x to the sixth over 720 minus x to the sixth over 720. So you end up with negative 121 x to the sixth over 720. So none of these canceled out, so here are our first four non-zero terms. Alright, our next part C says, now find the value of f6 of 0. Now the reason it's 0 is, if you remember, we are focused on x equals 0. So it's the Maclaurin series at 0. So basically we want the sixth power term, which is really, so sixth derivative is the sixth power term, right? And it actually turns out that we do have the sixth power term, right? Or the sixth derivative. So even though it's technically a four-term Taylor series, it's not including those zeros. So that right there, the sixth derivative is the sixth power term, so that's what we need. So we just need to plug that guy in to our, we're basically finding m, right? So we're trying to find what the sixth term is at 0. Not finding m. We're finding the sixth derivative at 0. So it's just, we're going to take our sixth term right there, our sixth derivative, which is 121 x to the sixth over 720. And we know that that stemmed from f to the sixth at 0, right? That 121 was f to the sixth at 0 over 6 factorial. So I'm doing some extra work because we already now know that the f to the sixth is 0, because remember, this is our term from our Taylor series. So what is f to the sixth of 0 equal to? 121. The only reason you would need to do this is if that 6 factorial changed. Remember when we did this up here? If that 6 factorial was what got changed to possibly a 3 factorial, if something got canceled out, then you would need to figure this out, because that means that number has did change. Okay, but you know that that's what this equals. If you multiply both sides by 720, that would cancel out. Divide both sides by x to the sixth, so you would end up with f sixth of 0 is actually 121. So this just wants you to find the sixth derivative at 0. Alright, next up, let P4 of x be the fourth degree polynomial for f about x equals 0. Using the information from the graph of y equals f5 of x shown above, show that P4 of 1/4 minus f of 1/4 is less than 1 over 3,000. So remember, this is just the error, correct? So that's just the error. So don't forget that. So we know that our error has to be less than or equal to, because it was a fourth degree polynomial, has to be less than or equal to f of 5 of x over 5 factorial x to the fifth. So I put the absolute values here just in case that's going to be negative in the graph. But it can be around the whole entire thing, right? So it depends on what if you're comfortable with reading it before or after. So now the question is, what is the error? So the error is going to be f5, the fifth derivative of x. At what term are we going to be focused on? So let's look at our graph, remembering that this is 1. So this is the graph of f5 to the x. So here is 1, this is 0.5, this is 0.25, 0.75. So which x are we worried about? The x that we're worried about is going to be at 1/4 over 5 factorial, which is 120, times x to the fifth, which again is going to be 1/4 to the fifth. So just moving here, our error is going to be less than or equal to, so what is f5 of the fourth? Knowing that they gave us the graph right here, so here's the quarter. We know that it's, so let's read the graph here, okay? Because it's not at 40, but this represents, right? Can we agree that this came from the max error? So we don't want the exact number because we don't know what that is. Okay, there's no way for us to figure out that number. But what we do know is that the max the error could be is 40. It's very close to 40, but it's not quite at 40. So we're going to say that the max, the actual value is unknown, but we know that it's less than 40. Does that make sense? I don't know what that value is, but I know it's less than 40. So I'm actually going to say that m5 of a quarter is going to be 40 over 120 times 1/4 to the fifth. Okay, and then when you do your math, you actually end up with 1 over 3072, and lo and behold, our error is less than 1 over 3000. So check. Okay, so don't forget that this guy right here represents the m, which means that it's the max value that the error can be. So just an important note, I have it right here, 1 second. Sometimes the value on the interval between our center C and our x value at which we would like to evaluate our function a is itself not explicitly given or nor easy to find. So in this case, we may choose the first known reasonable rational number that is greater than our next derivative of that point. So if we choose a number that is too large, we defeat the purpose of the error bound. But if we choose a value smaller than this, there is no guarantee that our approximation will fall in our interval. So we have to pick one that's a little bit greater but not too far off, which is what we just did in this example. Alright, moving on to example 4. So example 4 says, the Taylor series about x equals 3 for a certain function f converges to f of x for all x in the interval of convergence between the fourth derivative being less than or equal to the fourth derivative of f of 3. For all x over 3, 4, the nth derivative of f at x equals 3 is given by that nth term. Okay? So, a lot of information, right? So we have the nth derivative of 3 right here. So we can actually figure out what f1 of 3, f0 of 3, f2 of 3, f3 of 3, f4 of 3, f5 of 3, and so on and so on. And we're given f of 3. So this we're going to come back to in just a second. Okay? Knowing that the interval of convergence and this statement for all x over 3/4. That's what we're trying to figure out. So let's come back to it. The first thing is what it asks us to do is write the fourth degree Taylor polynomial for f about x equals 3. So the fourth degree means that we have to go all the way to n equals 4, right? So we already know what the function of 3 is. So we start with this. So at n equals 0, it's 1/3. So right now we're writing the p4 of x, right? Plus, what is our n equals 1? What is our n equals 2? What is our n equals 3? And what is our n equals 4? So we want to go to fourth degree, so that means to the fourth derivative. Okay? How do we figure that out? Well, we have the nth term, so literally I just need to plug this in. So f1, when n is 1 of 3, is equal to -1 to 1 of 1 factorial over 5 times 1 plus 3, which is 4. So that will give us -1 over 120. So over here, I'm going to write -1 over 120 times x minus 3, right, because it's centered at 3. All of that over technically 1 factorial. We'll clean that up in a sec. Now to find f2 of 3, we do the same thing. So it's -1 squared times 2 factorial over 5 squared times 5. So we end up with, once we do the math, 2 over 125. So let's do it for all of them. F of 3, when you do the same thing, you get -6 over 750. When you do it for f of 4, you get 24 over 4,375. So let's plug all these in. So here it's 2 over 125, x minus 3 squared over 2 factorial. -6 plus -6 over 750, x minus 5 cubed over 3 factorial. Plus the last one, which is 24 over 4375, x minus 5 to the 4th over 4 factorial. So when you clean this up, just to make it look a little bit prettier, you get 1/3 minus 1 over 120, x minus 3, plus 2. Why'd I put 120? Oh, I don't know why I did that. 5 times 4 is 20, guys. Sorry. 5 times 4 is 20. So that's going to be 20. Alright, plus, when you simplify this, you end up with 1 over 125 x minus 3 squared minus, when you simplify this, you get 1 over 750 x minus 5 cubed plus 1 over 4375 x minus 3 to the fourth. So a lot of it was just simplifying. Part B. Find the radius of convergence of the Taylor series for f about x equals 3. So what does that mean? We want to find the radius of convergence for the Taylor series at x equals 3. Here's our Taylor series. So what do you think we got to do to this ratio test? Okay, so you're going to be doing the limit. Trying to clean this up. So you're going to do the limit as n approaches infinity. Trying to see what is left. No, I messed this up. I'm sorry, guys. Alright, we're already at 22 minutes. Let's leave this for in class, and then, because I really need to review this before I think of teaching it to you. The last part down here, show that the third degree Taylor polynomial approximates f of 4 with an error less than 1 over 400. So you basically have to go and figure out what is your maximum error for the fourth derivative, because this is third degree, over 4 prime times your x minus 3 to the fourth. So we know that our x is going to be 4 that we're focusing on. And then you just figure this out. We know what the f4 of 4 is. Okay, we know what this is at 3. So that would be the maximum error that we can figure out. And that's where this comes in, is that we know that the f of 4 of x is actually going to be less than or equal to f4 of 3. So that's why, even though we don't know what f4 of 4 is, we know that it's less than this. So that means our max error is going to be this 24 over 4375 over 4 factorial times 4 minus 3. We're still going to plug in that 4 over here. So that's 1 to the fourth. And once you figure that out, you get 1 over 4375, which is less than 1 over 4,000. Okay. All right, and then this last one, we already did part A and part B in class together, so we'll do part C in class together as with part B. All right, enjoy.